Hi everyone. This is a talk I'll be giving the second week of class in Hong Kong. It's down here in the lower left, the Asia South Pacific Design Automation Conference. There's a main design automation conference that's held in the US. I highly recommend that conference. It's the place to be for the field of design automation. So that's the software we use to design chips. And there's stacks of a wide variety of software tools we need for various reasons. Down at the transistor level, you've got SPICE. What is that? Simulation program with integrated circuit emphasis. That's back from, I believe, like the 1960s or 70s. But that is where you model a transistor with parameters that you kind of can understand. So the mobility and the gate oxide thickness. And then you've got, up at the high level, system level tools that say, hey, I want to make a GPU that goes this fast. Then there's tools that go through the whole stack. Well, you want it this fast, you need this amount of memory. It will drop into the different elements. So you need an adder, and it needs to be this fast. And the adder is mimic with the transistors. Generally speaking, logic is built out of what we call standard cells. So there's software that does the synthesis of your design intent to standard cells, places all the cells, and then routes the wires. So synthesis, place, and route is a big part of the design automation ecosystem, but tons of stuff in this conference. I happen to be able to have been invited to give the talk in the occasion of the 100th anniversary of the invention of the FET. So the patent up here from Lilienfeld, 1926 was the filing date. So 100 years of the FET, and I'm a history buff, as you probably already figured out. So this is going to be fun for me. Now, you might be thinking, hey, Greg, this is cheating. You're already getting paid to do this talk in the sense of the travel is paid. But I want you to notice that this is a 21-minute talk for audiences that understand, these professional audiences have been doing this for a while. So let's see how long I take, where I'm going to try and stop and show you the elements on the slides. And your homework assignment is each of you should come up with 2 or 3 questions of something you think is important that you didn't understand. I either skipped over it or how I explained it was not working for you. So that's the homework assignment. Let's see if we can head off some questions here right away. At the upper right, this is a modern gate-all-around FET. So this is a cross-section of a wafer. The horizontal rectangles are your channels. So the current is going in and out of your screen, and wrapping around those is the gate material. We talk about those, of course, in the class later. For this particular talk, I wanted to first acknowledge another anniversary. This is a film where it was filmed in 1926, so 100 years ago. Metropolis was the first cinematic depiction of a robot. And it actually was set this year, so 100 years in the future. So let's give ourselves a report card. Well, the report card's mixed. On the right, we see all these kinds of attempts at early robots. Of course, on the left, this is a recent concert with these stage dancing robots. They're pretty impressive. So mixed report card. All of this built on, of course, the FET and as it relates to image recognition and machine intelligence and all this stuff. So let's talk about the FET in a little more detail and talk. This is J.E. Lilienfeld was the inventor of this idea, field effect transistor. I can use transistors to do all kinds of new stuff and great stuff at this point, 100 years later. For instance, as far as I can tell, this is the one picture that exists of Lilienfeld. And you can see there's like a stamp maybe from a, passport or something. I can clean all that up and modernize it with AI, right? The diffusion models in AI. So here we go, hopefully. And that's pretty impressive, but I don't have to stop there. I can, with a prompt, have AI show me him in his lab in the 1920s. In this era, radio and vacuum tubes were the thing. And this, the great idea here was a replacement, improvement for the vacuum tube. Now, to generate this picture from a prompt, ChatGPT's GPT's estimate of itself is that this took about 20 trillion FETs from my own laptop down into the up into the data center and the LLM model and the diffusion model. So 20 trillion transistors just to make one picture, which is an enormous amount of transistors. But when you look at what we're doing today in the world, a low estimate is that we're making 20 trillion FETs per second in the world. So all of us on the world, we get 2,500 new FETs every second. So this is the most successful thing that humankind has made. It permeates all kinds of things already before we get into maybe the heart of the AI era coming up. So what made the FET so successful? The first, sorry about the Windows excited about it, installing some software. What made the FET so successful? As I mentioned, in this era, it was all about radio, vacuum tubes, and radio frequency. You need gain to amplify signals. You need input impedance to make the different circuits. He understood that his invention would be good at this. So that's number one. Is it has some of the basic, three-terminal triode is a term for three-terminal device characteristics that you would need. Furthermore, he just really wanted to get rid of the vacuum tube. It's big, it's power hungry, doesn't last very long. What he could not have foreseen is before people could successfully make his invention, the computing era showed up. So people had to start the computing era with vacuum tubes. When you put 18,000 vacuum tubes together, like in this ENIAC computer, the mean time between failures was about half a day. So it was just very, very difficult to do computing with the vacuum tubes. Now, it was not the case in the 1940s and 50s for the transistor, but ultimately, the fact that a transistor is solid state, so it doesn't need a vacuum that can leak, or in a mechanical relay, a moving part. The solid state nature of his invention led to the reliability. That was one of the big things that really pushed the FET into its prominence. One of the other things that Lilienfeld understood is he wanted to scale the dimensions of his invention, because he understood make this smaller, reduce the capacitance, reduce the voltage, lower the power, all that's good. And so that you see in his diagram here, you've got a source, a gate, and a drain. He's not calling them that, but that's what his invention is showing here. And he's saying, we need to reduce these dimensions. And actually, he had an idea for that in his patent. It's not widely discussed. I guess not a lot of people read this thing. Is this 14. So 14 is actually that's a squiggly line, is a crack in a glass substrate. So you're putting the semiconductor on top of the glass substrate, you crack the glass, you insert a strip of aluminum foil, and now you've got yourself a backgate to the device. That is a very small dimension. Backgate is something we probably will encounter if we talk about new device research. It's a convenient way to make a gate, the gate signal to a semiconductor film in a lab, but gates coming from the back lack often a property called self-alignment to other parts, like the contacts of the transistor. So self-alignment of features is a major part of nanometer era process nodes, and you don't really get that when you do the backgate. So if you don't encounter that in this semester's processing class, or maybe you already did in the last semester, if the concept of self-alignment is not apparent to you, let's be sure to talk about that. You can't really divorce the processing from the device in any modern era transistor. Let's scale in on the real part here, the actual transistor, scale it up a bit. In his case, the semiconductor was copper sulfide, and then you've got this aluminum foil backgate that's going to create the electric field here. And he was already thinking ahead. I'm using aluminum foil because it's small. In fact, he was already thinking ahead, basically to the nanometer era. So give him a lot of credit for 100 years ago, thinking of a way to really make these things small. And small in a field effect transistor, small means lower capacitance, and that means often also lower voltage, so everything is great about power and speed that way. Formally, in the MOSFET era, the way you get lower delay and lower power by reducing the dimensions. It was codified by Robert Dennard, and it's called Dennard scaling, and I will talk about that in the class, I'm sure. But the scale dimension aspect, Lilienfeld was already thinking about this and already had us a great idea for doing that. Now, he could have, now this is a broad plot of computing devices in history. Babbage is an analytical engine, Hollerith, Zeus is an amazing forgotten man in Germany. You get into the vacuum tubes, we saw in our case the ENIAC. Then you get into the transistor era, so single transistors, wired onto boards, made very successful computers for a while. Then you get into the transistor, beyond the transistor era, the point where I'm sure Lilienfeld could not have comprehended. So individual transistors, yes, he could have certainly foreseen something along that. Integrated circuits, not so much. The 4004 from Intel being the first big integrated circuit. And then from then on, we refer to it as this massively successful decades of what we call Moore's Law. So Gordon Moore, originally at Fairchild Semiconductor, then off and running, he went to Intel and never looked back. So I want to talk about the power of scaling. When you zoom out this far, it's hard to really appreciate it. But if I just take the time in this red band here, that encompasses actually 6 different Moore's Law nodes, because I'm skipping, in the pictures, I'm skipping the nodes that are in the vertical text here. So 180, 130 to 90, blah, blah, blah. So each time I skip a node, then I'm doing a 1/4 area, because Moore's Law is 1/2 the area every node. Another fact is people versed in the art understand that when I'm showing these pictures, I'm talking about SRAM, bit cells. This is an SRAM bit cell. SRAM, and we'll talk about this actually further in this talk, but in the course, uses 6 transistors to store a bit. And so the transistors, the features on the top are the gate features, and then underneath them are the active regions, diffusion in the old days into silicon, and then isolation oxide is the field oxide. So wherever you have a gate crossing the diffusion, you've got a transistor. So 1, 2, 3, 4, 5, 6, and then you'd have 2 P transistors, P diffusion, 2 N transistors in the bit cell like a prison cell. And then this strip of communication out to the outside world, turns on and off the ability to communicate the bit state to the outside world, or the other way around, program the bit. That's called the word line, and that's just because a collection of bits along this line becomes a word in architecture speak. So long story short, look at this, bit cells are shrinking great. They switched their form factor in modern processes where you really could only do straight lines with the limitations of modern lithography. So when you look back at this older node, you see, we made the gate wider here because we want a little more room to stick a contact on there where we know there's going to be some misalignment over the process. So with a little more room there, and then the source and drain contact, bubble this out a little bit, make a little bit more room for the contact to land there. You don't get any of that in the modern era. So these bit cells that show the straight lines are less efficient area-wise than these, but it's just we're enabling Moore's Law, so we came out ahead. Anyway, 6 Moore's Law nodes, 12 years. This is exactly what you expect when Moore's Law is firing in all cylinders. So the scalability, when you blow it up over decades, just an amazing feature of FET that made it a success. The particular band of time that I picked here, in hindsight, these things may not seem that big of a deal to you, but in the industry at the time, these look like they might be showstoppers. Like, we can't do this, and figure out how to keep Moore's Law going. Switching from aluminum to copper, from a resistance and reliability standpoint, copper, you can't etch it chemically very well. So we went to a chemical mechanical polishing, CMP, damascene process to make the copper, and that's all kinds of yield and reliability problems. People actually shipped copper parts in the early days of copper that failed at the customer sites because of things we couldn't foresee, had to improve the processes. Strain engineering, we're definitely going to talk about that. as we shrunk the transistors, we kind of ran out of performance for various reasons that we'll sure talk about in the class. And the way to buy back some performance was some very innovative folks figured out you could physically strain, pushing or pulling, tensile stress, the silicon lattice and improve the mobility of the fundamental semiconductor. So we built in strain engineering, strain layers and such. We'll talk about that. It's more of a process thing, but we definitely want to talk about it on a device performance level as well. And then also in this era was the high K metal gate. So the dielectric constant of the silicon oxide, as we shrunk the device or had trouble shrinking the device, that we couldn't build enough electric field with the voltages we wanted with that dielectric constant. So we went to higher K, hafnium oxide most commonly, so that for a given voltage we could develop more electric field across the dielectric, the gate dielectric, and then influence the on-off characteristics of the device better. Major thing in industry where there was an uncertainty about how to do the processing of this new material. You could do it where you put the dielectric first down and then the gate, which is, sounds obvious, but there's also a way to do it where you put the gate, a dummy gate down first, then you remove that and you do the dielectric. And Intel and TSMC at the time picked different ways to do it, gate first, gate last. TSMC picked wrong, and that's why they had to quickly go from what they were calling their 32 nanometer node to a kind of half-step 28 nanometer node to go back and fix it because they just made the wrong bet and they got behind. And then the last big innovation, which I point out at this conference, because Chin-Ming Hu, the leader of the group at Berkeley that invented the FinFET, gave an invited talk here as well at this conference. So 4 major parts of the semiconductor technology of MOSFETs right in this tiny little band of scaling in Moore's law. Now, if we go forward to today's pitches, so down into the 45 nanometer, a pitch, again, if this hasn't come up in your class, let's just make sure. The width of a line when you print it will vary day to day, or parts of the wafer, parts of the die, when you have variations in how long you expose it, or how old the resist is, the light bulb, in case lasers in modern day. The actual width of a line will go up and down. Now, the space between spaces will go down and up exactly the same amount, right? You're not changing the pitch, which is one edge, like a left edge of the device to the next left edge of the device. That's the pitch. That never changes, and that's why we often say that word, as opposed to what we really want to look at, which is how big is the gate. So anyway, pitch of 45 nanometers, or in the 40s, that means we can fit 56 contacted pitch gates. So sometimes putting a contact down requires you to make the gates spread them farther apart. So the way to make an active circuit is to contact it. So that's shorthand for this is transistors that you can actually use, as opposed to if you didn't put a contact in, sometimes you can cram in there a little bit more. So anyway, 56 contacted pitch gates in that width of the aluminum foil that Lilienfeld was so clever to put in now. Let's see what he thinks about the amazing era that we've found ourselves at this point where we can do such a small transistor. Well, through AI, of course. He's very impressed. Now, there's still a lot to improve in AI. I'll show you my example from preparing for this talk. I had this picture made by, in this case, Gemini, and all I wanted was aluminum foil to be on one line. So I was like, hey, put the aluminum and the foil on one line. And it didn't do it right. I said, no, that's not right, do it again. I said, well, what about this? Come on, it's not even close. So the whole conversation went along where, I'm trying to do that. It comes up with random pictures. Like, no, go back. You're dropping lines, you're dropping words. Oh, how about a mountain? No. And then finally I just give up. Say, look, get rid of all the text. No, you forgot. Get rid of all the text. I'll just do it myself. So in my opinion, room for improvement in AI. How do we improve AI? Right now it typically means bigger models needing more transistors. So that brings the question then, what's next? How do we continue to scale the transistor going forward? Now, we know what basically the next decade holds, where we are producing 2 nanometer silicon. I know TSMC's announced this. The 18A from Intel has been announced. Generally, we've moved from the FinFET era into the gate-all-around era, like the actual picture I showed you at the beginning of the talk. There's a slightly more compact form of the gate-all-around called a fork sheet. This is, I believe, an IMEC actual invention. So it's a kind of a little small step that you get in density. Then the big one going forward in a few years is to stack N gate-all-around FET stripes on top of P, or the other way around. So the way we refer to CMOS logic as complementary, in the sense that you have a P and an N device that complement each other in the circuits. Now we're just saying, well, let's do the complementary part in the actual FET. So looking down on the wafer, you're going to see what looks like one transistor is actually one buried under another one, so you get a boost that way. The height of this is going to be a problem. You can imagine how deep a contact needs to be to get down to the bottom-most gate-all-around feature. And then the capacitance between the contact and the gate is going to be bad when it gets bigger. So one next step that we're already researching and looks promising is to collapse the height of those gate-all-around channels to 2-dimensional semiconductors. So atomic, in this case, in IMEX terminology, but 2D CMOS, 2D MOS. That's what a lot of people work on. But that's the whole next decade. We kind of know what's happening there. And unfortunately, we also know what's going to go on with our speed and our performance. It's not going to be great. In order to talk about that, I go back to this, for me, this paper by Professor Philip Wong at Stanford, where back in the 90 nanometer node regime, he said, hey, we know the intrinsic gate capacitance, so the gate oxide down to the silicon, that capacitance, we're going to make it smaller, we're going to shrink it. But all these parasitic capacitors don't scale, or even reverse scale. So quickly, we're going to go from a majority of the capacitance that we want, ideally in the intrinsic capacitance, is going to switch. The intrinsic capacitance is going to switch to being a minority of the overall capacitance. So we can't control the fringing capacitance from, say, the side of the gate here in light blue down to the silicon. And of course, this is written before the FinFET, but the FinFET doesn't get any better. It's a lot worse, right, when you think about the geometries. And then the capacitance of the contact, or plug, sometimes it's called, to the gate. And of course, we're shrinking that dimension. Now, you can ameliorate this a bit by, this gray space going to a lower K. So you want higher K where you're actually intending to create a field to switch it. You want lower K in the back end of line between the metals and what have you. So that is one way to make progress. But silicon K is 3.9, vacuum's 1. We're never going to do better than that. So there's not an infinite amount of help we can get out of a lot of trouble for going to lower K materials. And it gets worse, the story. So in these little boxes, the pictures of the FET, now the intrinsic capacitance is a minority of the overall capacitance built into this actual FET. So this would be a device we'd model in our design automation software. But when you want to connect 2 transistors to each other, the wire capacitance between them in the 7 nanometer node on down is actually a majority of the problem, and the minority of the problem is the actual transistors. And this is something we just, it's hard to get around. In this plot I'm showing on the left, that's the gate length over time, and then the logic voltage, which we'll get to. It's famously, we're not scaling the gate length like we like to, according to Moore's law and then Dennard scaling. But that's really actually not that big of a problem, given all the parasitic capacitances are dominating. But what you also have here, outside of looking at an individual transistor, is this parasitic connection capacitance. And that's going to get lumped into the C of a circuit, where the CV over I has the units of time, so that's your delay metric. And then power has the CV squared F is the units of power. So every time you switch a circuit, you're going to burn power, and it's going to be proportional to the square of the voltage and the capacitance. And of course, if you have resistance, it just gets worse. So big problem in modern nodes because we just shrunk the FET so successfully. When people talk about FETs, they tend to be focusing on the logic paths, like how fast can I make this circuit, and that's going to fold into the gigahertz of a CPU or what have you. But I wanted to stop and talk about the other class of use of transistors. Used AI here to imagine aging Lilienfeld along the way, and of course, when we get older, we often have memory problems, and that's definitely what we have with the transistors. So there are three main kinds of memory that we use, the big established three. Each one uses the FET. And so scaling in the memory regime is as big a problem as the logic, if not more. So talked about the SRAM from a top-down view. This is the circuit representation. So you have these this vertical connection, this gate shape that we saw before. That's going to be the word line to both of these pass gates. They're passing the signal in and out. And then there's a PN combination, what we call cross-coupled to each other. That's an unstable circuit. So it's going to basically flip or flop between a 1 and a 0 state, a high and a low voltage, where the high voltage is coming in here, this power supply is coming in here. So it's going to flip one way or another and then stay there. And we can influence which way it flips with the outside influence. That's this 6 transistor, 6T standard memory cell for a standard SRAM. And we're going to talk about that here in a second. You also have DRAM, which is simple from a circuit standpoint. You have one pass gate opening up access to a capacitor. So you just drive your voltage, which is going to fill up your capacitor with electrons, close it off, and it'll sit there. It'll leak. The capacitor will leak. In modern nanometer circuitry because you make the gate oxide small and what have you. So it forgets what it's doing, and then you have to refresh it. I think I'm going to talk about that, or may have already. We'll see how it goes. I think I might not get there by the time you hear this. Let's talk about DRAM a little bit. And then the last one is flash. This is ingenious, where you actually are tunneling electrons from the channel here up into a floating gate. So this is a piece of silicon that's not connected to anything. So once it's sandwiched between two dielectric layers, so the sandwich between the gate electrode and the substrate electrode is a metal or polysilicon feature, a dielectric, another floating gate, another dielectric, and then the channel. And they'll get stuck in that floating gate until you want to tunnel them back, push them back out. So that's a non-volatile memory compared to DRAM, which is very useful. When you've got, at some point, you lose the power to the data center, you want to remember some stuff, or your pictures on your phone. So we've got these three classes of memory. 90% of the 20 trillion transistors in the act of creating this picture, for instance, or the picture I referenced, those are memory. So memory is the big use, the big problem. And let's take a look and see how we're doing with the memory. Actually, let me stop. I have another nod to Lilienfeld here, where he's, of course, known for inventing this transistor concept, the FET transistor concept. And people might say, well, this is a much more advanced version of a transistor, so we can't give Lilienfeld all the credit for that thing, and that's of course not the case. This is pretty cool. So when I say tunneling, I literally mean quantum mechanical tunneling through a barrier. So this is flash memory. It may be the first use of a quantum mechanical effect in electronics. I don't know that that's true, but it very well may be. It's the first that I know of where you're using quantum mechanical tunneling principles. Fowler and Nordheim, so Fowler-Nordheim tunneling is named, they formalized this concept, but really what they were doing was actually figuring out what was happening by the initial observation of Lilienfeld, because you can tunnel not necessarily just through a dielectric, but also through the vacuum of a vacuum tube. And then the one other thing on this plot that's not a transistor is, okay, there's one thing Lilienfeld didn't influence. Actually, he invented the dry electrolytic capacitor, which was used for a century. We don't really use it anymore. I think there's some improvements, but for almost a century after his invention, it was used here. So very successful inventor. 60 patents, 15 German patents, had a productive career. I made this AI picture as imagining an aged Lilienfeld using a cane. So this is your mobility enhancement pun. But then I realized after I was reading about his life, one other thing that made him smarter than we thought is this was not how he retired. He retired to the Virgin Islands. And his last many years was in the beautiful sun and water of the Virgin Islands. And actually, another interesting piece of trivia about him is, even though he was this successful, when he passed away, his widow granted a very large prize. I think there's only 2 fully funded prizes in the American Physical Society, and one of them is the Lilienfeld Prize, which pays for the expenses for someone to give 3 talks about their technology. Was a big deal to the American Physical Society, but when they got this donation, they had to go look up who is Lilienfeld, because he wasn't well known. This kind of was forgotten in history for a while, so they had to look him up, figure out who he was. Luckily, we all understand the greatness of his invention 100 years later. So specifically about the 3 kinds of memory and the challenges we have. So SRAM, this is the bit cell area, so the area of those 6 transistors as we go through the process nodes. These are the numbers in nanometers. The numbers divorced from reality in terms of what actually was the actual dimensions. Back in the olden days, when I did this stuff, you had the gate length was actually pretty much the gate node or the process node, and we've still shrunk the cells, even though we haven't been shrinking the gate length as much. But these are the node numbers, not reflective of the physical dimensions per se, but reflective of, the next node got smaller than the last one. But very famously in our industry, the 3 nanometer TSMC bit cell was the same size as the 5 nanometer, so Moore's law stopped. And actually, I believe that the 2 nanometer bit cell is actually also the same size as the 3 nanometer bit cell. They just did some stuff in the circuitry that made it the full memory size. When you amortize the peripheral circuitry around it area, you get a reduction. So in SRAM, Moore's law has stopped, and this is a big deal. Memory near the computational logic transistors is the most important memory. This is actually just the bit cell size. So the wafer cost has really been going up a lot lately. So when you factor in the wafer cost and figure out what your price per bit, or in this case megabyte, MB, it's actually going the wrong way. It's not just stopped. You're paying more for an SRAM transistor today than you were before, which is crazy, right? People do it because they want access to say the logic transistors, but this is a really bad situation in the SRAM scaling. What is going on there is the variation of the transistors affects how stable that flip of the logic, those cross-coupled transistors. It's really the variation that's the problem. So they start to vary more as they get smaller, and you can intuitively kind of understand this as the stepper has a variation. It can print widths of lines. It's going to vary around that number, and if you use the same stepper for a future node, the variation, the full variation number is not going to change, but the percentage of variation in a smaller transistor is going to go up. So, and there's other reasons why you have variation, random dopant variation and stuff like that. So anyway, that's the problem, is that the SRAM bits are just not stable. You can't make a working SRAM if you make it any smaller than we have today, unless you do something to reduce variation. DRAM. So DRAM's been around forever. Dennard, who formalized the scaling rules of transistors, also invented the DRAM. Another great guy to look up, Robert Dennard. I'm sure I'll mention him a few times. So it's been going on so long that this plot goes over so many years that you really have to zoom in here at the right and formally observe here that we're 2 orders of magnitude off where we thought we would be just back in, say, 2010. In DRAM scaling has just been really slowed down lately. We'll talk about DRAM, of course, in the course. And Flash. Flash's huge story is back in this time frame, the flash bit stopped scaling. The transistor stopped scaling. So the only way to make more bits per dollar was to stack bits on top of each other, these layers, and then combine some of the processing like the contact and the channel features could be drilled in common across an entire, through an entire stack, and that saves money. So we have this massive stacking story where 24-layer vertical NAND was introduced here by Samsung. Today I think we're at over 300, or at least at the high 200s in terms of layers in one stack. And now they're talking about making multiple stacks on top of one another. But even with all, this is amazing, amazing technology. It's really crazy that we're able to do this. Even with all that, we're way off of Moore's Law in the last couple of decades in terms of the cost of flash. Now, be careful here. Here I'm talking about the price, which is different than the cost. So, in fact, why you have a dip here is the pandemic. So people bought a bunch of flash memory, pandemic ended, and people didn't want to buy as much anymore, so there was a bit of a crisis in the industry for a while. And then now with DRAM, let's go back to DRAM. With DRAM, probably a lot of the pressure here is not the underlying cost as much as AI needs DRAM so much that the DRAM makers can charge a little more than, more profit. So be careful on price versus cost, but that the price data is what is available readily. Now, what do we really want? We don't want to do this pyramid of memories, and this is another thing we'll get into in the course, but basically SRAM's too expensive to get all the bits you want, so you go to a cheaper layer in DRAM, so you get it's slower and cheaper. And then flash is even slower and cheaper still. So there's a stack where you use more memory as you go down the pyramid. So this memory pyramid is just something you're just going to see in every conference talk for the rest of your life. I apologize in advance, but that is the picture here. What we want to do, ideally, is not have stuff in DRAM off on another chip. Just have enough bits on the chip. You can't really fit a modern LLM all onto even a hypothetically scaled magic memory, but you get closer, and the more of a model you can get onto the chip, the faster you're going to go. So we have, we have what we as users of these transistors need, which is super fast, super low energy, energy then speed here, small, so get as many as possible on a wafer. You need 8 sigmas. So in terms of a Gaussian distribution, one of the big buzzwords forever in the industry was 6 sigma, and that was what companies like Motorola used to do process control, modern process control. Japan really pushed this a lot in the 80s. But when you count out the number of bits you have on a chip, you need to go to even a higher degree of control. So you need to go 8 standard deviations below the mean, and whatever that amount of variation is still needs to give you what we call a memory window, which is the ability to discern one bit from another bit given maximum variation between 2 bits. I'll talk about this in the class, or at least a guest speaker hopefully will, so don't worry about that too much. Endurance, so anything built on the silicon FET is basically has infinite endurance, because we know how to make a FET that can we know how to make a reliable FET. Some of the newer technologies, especially the non-volatile ones, flash being a great case, do not have a long endurance. In fact, flash natively gets you to about 1 million cycles. So, programming a 1, programming a 0, programming a 1, programming a 0, that's 4 cycles. So you only get 10 million cycles in some of these flash products. So that, the thumb drive you put in your laptop, for instance, it knows bits are going to fail. So you're buying like twice as many bits as it says you are, because as bits fail, it's going to monitor for that and then replace bad bits with good bits. And then also the error is typically just the threshold voltage of the device after you program it isn't where you want it. So there are these really complex programming algorithms to say, I'm going to program a 1, check it, didn't quite get there, so I'm going to push it a little bit harder. So there's a lot of stuff under the hood in this, really cheap flash memory that you buy. Of course, with solid state drives, they can put more expensive controls in there, but there's a lot going on under the hood there. And we'll talk about other non-volatile candidate non-volatile memories, and endurance is always going to be a question mark for them. And then up until today, CMOS compatibility is a big issue. So when you've got we've got a transistor on a wafer, and we want to put a new type of memory, call it a resistive RAM, which is a class we'll talk about. That, you can't use you might want a 1500 degree C anneal to make the crystal kind of recrystallize after you deposit it. And you can't, CMOS, after you put wires down on the CMOS logic, those wires really can't tolerate anything over 400 degrees C. So you have a kind of 400 degree C cap on anything you want to process on the wafer, and then other things like impurities. So if the memory you're using is, it can't be made out of gold, because gold diffuses really quickly through oxide, gets down into the silicon, and then becomes a deep level trap. So all of those things you hopefully will learn, traps and such, either in this class, or I think we might have touched on it a little bit in the previous class. So CMOS compatibility, and then non-volatile. We love non-volatile. We can make volatile memories work, of course, with DRAM and SRAM. So let's look at some of these candidate memories. One of the first ones to be invented was the resistive RAM. This is not an elegant technology, at least in the first instances of it, where you're really taking an oxide, in this case tantalum oxide, and so this is, you're making basically a capacitor, so metal, insulator metal, and if you put a high enough voltage, if you have a rough surface that the dielectric is sticking on, so you're going to get little bumps, and the bumps are going to be concentration bumps in the metal, and the bumps are geometrically going to concentrate electric field. And so the bumps are going to be, as you increase voltage, they're going to be high enough electric field where they start to break the oxide. Ironically, what was in Lilienfeld's original patent, but break the oxide, and you can actually create a metal filament if you keep pushing between the two plates of metal. Pushes a crack right through the whole dielectric. Now, if it goes all the way to the other plate, you can't undo that often. So you can't push a field the other way and push the metal ions out the other way. So you kind of go halfway. But what you've done basically is reduce the resistance that you measure because the filament's gone partway through the oxide, and that is the program, the resistance changes the program in there. Now, tons of stuff that's gone on in not formal metal cracks, sometimes it's defects, and tons of stuff to talk about. We'll talk about that more, but the point here in this talk is look at the number of decades we've been working on this, and we haven't solved things we want in a memory. Now, it's very, very promising stuff. So TSMC, actually, you can buy a 22 nanometer ReRAM at a TSMC foundry, and there are some really interesting potential future nodes, but nothing at the state of the art, 2-3 nanometers. The other big class is ferroelectric memory. We're going to talk about that for sure. It's gone through a couple of different types. SBT is just the material, strontium bismuth titanate. Was a big success story for a while. And then the big thing that came up, which was an accident, accident's probably not the right word, but basically unintended discovery in Germany was that you could strain, and we talked about straining the silicon in the channel. A student in Germany found that you could strain the dielectric to make it ferroelectric, and in interest of not making this a 3-hour talk, I won't talk about ferroelectricity, but it's just we'll talk about it in a future lecture, but it's just typically a structure that, like an atomic structure where the electric field can actually move a crystal ion, and that changes the electrical characteristics of the dielectric back and forth. But again, decades and decades of work, and not universal memory still have problems. Lots of promising work. Ferroelectric's a very promising field. And then the last big one in what we call the emerging non-volatile memory space, ENVM, is the magnetic RAMs. Started again decades ago. It's gone through different embodiments. There are products that you can buy. Everspin is one company. You can buy this at Samsung. You can buy it at TSMC for older nodes. Spin transfer torque, STT. And then there is research in a spin orbit torque. This is just you're playing with the magnetic properties of a material and changing the resistance just like you do circuit-wise in the ReRAMers, doing it with this magnetic effect. Again, not anything at the state of the art that is fast enough and low power enough and has the endurance and all the things you need to replace SRAM at this point. In fact, one of my favorite quotes about how difficult this field is comes from IBM. They were, I believe, jumped on the MRAM bandwagon first. The quote here from 2021 even is, hey, we want to replace cache. Last level cache is the architecturally still the SRAM on a chip, but there's even, I talked about the memory pyramid. There's parts of the pyramid I didn't show, which are, there's things called register files, which are the fastest, most expensive way to store a bit. Then there's a first level cache, then there's a second level cache, then there's a third level cache. And that's architecturally what you do to optimize for the fact that even SRAM, you can't place all the data you want. So you place what you think is going to be important in lower level caches. And then when the chip needs a piece of data, you go look for it in the first level cache. And if you can't find it, you stop and go to the next level. And it on a nanoscale, it's a massive, massive delay. But even the last level cache works, in the many megahertz range. So from a chip operation standpoint, you still get what you need done. But anyway, IBM saying, hey, we've been working on cache replacement. They're trying to replace the 6 transistor 6T SRAM with a MRAM. And the MRAM you can make with it's just a resistor with an access transistor. So like the DRAM, it's a 1T, 1R bit cell. DRAM is 1T, 1C, SRAM is 6T. So just intuitively, 1T is 6 times smaller than a 6T bit cell if you can stack the resistor right on top of the transistor. Anyway, this lack of being able to scale logic and memory is a problem because of AI. So this is, again, very zoomed out. So we go back to the perceptron, which is the first machine really credited with being a modern AI architecture, through AlexNet, which was the big flashbulb moment where people realized that AI was for real, and then up into the modern era. Now be careful with this plot where already log plots, the brain can't understand log plots, what it means, we're plotting exponentials. But here, there's 4 orders of magnitude between each dashed line. So just in the last 10 years, the growth in the need for the number of computations to train in AI, so floating point operations per second is a flop. That's the computer architecture benchmark for doing a piece of math. It's going up orders and orders of magnitude in the last few years. And then, of course, you need data centers that need from megawatts now to gigawatts, and we're going to ruin the planet, and we're never going to get where we need to go with AI if we don't make more efficient transistors. So you look at that whole explosion of AI is just this little piece of a time scale compared to the time it's taken to make new memory technologies, and they're not even done yet. Then you look at actually the data center power consumption. So going from the point at which it was less, data center power use in the US was less than 2% of the overall electricity consumption in the US to what the higher bound is looking more likely here. So 10%, say 2% to 10%. You look at that time frame, that's just here. And you look at that compared to how long it takes to make new technologies happen in semiconductors. So we've got to find better ways to accelerate semiconductor technology. That has been, that was my purpose when I went to this most recent job. And I lived through that. Of course, I was at a memory startup before that even. So I know there are ways to do this better. We need to be a lot more focused, and some of the costs of building infrastructure that really would help the ecosystem of inventors, technology inventors, is expensive and is kind of at the government level. I don't know that any one university or one company is going to put this stuff together that needs to get done, but we have to do it. And there are three vectors of progress we can focus on. One vector, let's just make we know we need to make the existing FETs better. That's limited in its ability to make progress, but it's what we know we can do now. Then we need to really accelerate things that are beyond the field effect transistor that could really get us to lower power computation. That's going to be some complicated technology, and then in often cases breaks the way we design circuits. So breaks the EDA software, which is a topic for this particular conference. And then the third is what I call advanced device system integration. One big topic here is heterogeneous 3D integration. So that's chips of different types stacked on top of one another can make a much more efficient system than just trying to put everything on one type of technology. So number one and number two, we know the roadmap, and we've got a lot of EDA problems in backside power delivery and how to route CFETs and model statistical variations more accurately to really ferret out what we call over-margining. So every step of the design process, you have uncertainty about how fast a device is going to run or how fast a circuit of device is going to run. So as an engineer, you say, okay, the mean of my simulation is this, and then I'm going to guard band up and down from that so that across any kind of process of variation, my circuit will still work. So I just simulate and make sure that my circuit is going to work at the slowest, what we call corner of the design of the transistor space, and the fastest corner. So we built in a bunch of margin. Now, the next person, so let's say the transistor person does that, then the circuit designer comes in, says, well, my circuit, I'm going to guard band a little bit, and then the system guy does. So because these software tools are discrete, independent tools, you often get over-margining because each one can't comprehend the margining that's been done previous step. So there's a lot of opportunity there just to reduce the power and the delay in circuits by really more accurately looking at the root causes of device variation. Now, in continuing the FET, I mentioned we've got the Moore's law reducing the gate length, where the gate length hasn't been doing that great. And then Dennard scaling says we need to reduce the voltage at the same rate, and we haven't been great at that either. So from a power and performance standpoint, the Dennard scaling equations are not looking that good. We know what the next 10 years looks like. So I'm plotting in red here, this is the power supply voltage. So we're already down in the 0.6 range. We're not going to get that much lower with the same transistors. That's obvious. There are things we can do. The 2D FET, 2D FETs ideally are going to have a lot lower variation than gate-all-arounds. And then things that I mentioned in the design in terms of variation reduction, but also things you can do in the process to reduce variation are going to be very important. And this could be poly grain structures, reduction of variations in dipoles. Going to get into that as a modern way to make a VT shift. There's a lot of things we can do in design and process just to make the existing transistor roadmap better. Then we get into fancy new transistors that promise to be able to be turned off and on better so that we can reduce the power supply and still get the performance we need. Carbon nanotube, so 2D is a sheet of something. Graphene was the big discovery. It's not a great semiconductor, it doesn't have a band gap. If you make a ribbon, a thin ribbon of graphene, the edge effects can actually make a band gap open up. But still, graphene, I don't think, doesn't look like that's where we're going to go. We're going in the 2D space to these TMDs, transition metal dichalcogenides, which is just a class of materials that can be semiconductors, which is a transition metal. So there's a part of the periodic chart that's molybdenum, tungsten. Those are transition metals. And then the chalcogenides are, that's actually just a Greek term for when they were digging up copper, they found these other materials. So the Greeks termed it born from copper, that's chalcogenide. That's selenium, sulfur, and some others. So tungsten, selenide, these kind of things, when you see those, that's a TMD, and that's the transition metal stuff that will probably be used in the 2D. 1D, we can roll the sheets up into tubes. And so the graphene, two-dimensional rolled up into a one-dimensional tube is a carbon nanotube, CNT. And that has no variation because it's there's no dimensional variation, for instance. There's not an edge. The problem is, at the moment, that there is a variation in the diameter of the tubes. And when you change the diameter of the tube, the atoms roll up and stitch in different ways. That's called chirality. And when they change the chirality based on different diameters, it actually can change from a metal to a semiconductor to an insulator. And you only want the semiconductor. So if you don't have perfect chirality, like every nanotube is the same, and you throw these things down on a wafer like pixie sticks, just toothpicks, one toothpick that's a metal is going to short out a circuit. So that's a problem with CNTs as they exist today. Tunneling FET is a way to allow the voltage to go down and still maintain the overall performance. Talk about those, I'm sure. Negative capacitance FET uses the ferroelectric property of the hafnium oxide, for instance, to get more performance out of a transistor. And then there's one of the holy grails in regular transistor field is a filter of the carriers that get injected. It's called cold source or a direct FET. We'll hopefully get into all that. But then longer term, what we really want to do is get the voltage down from 0.6 to 0.1, and that's probably not going to be an FET. So there are things that already operate at 10 millivolts or 20 millivolts. Superconducting logic is one. That is the same device as is used in quantum computers, or the one type of quantum computers, the type that IBM, Google, and Intel are all using right now is the Josephson junction. You can make a qubit, a quantum bit out of that, and you can also make a switch, a resistive switch. So that operates at 10 millivolts and also needs to be very cold. So that's a problem. You're not going to put that in a phone. You could cryogenically cool a data center and hypothetically come out ahead. So people are looking at that. Quantum dots, spin wave is the NRAM effect that's used in the memory. You can also make that into a logic device. What you're going to see with the superconducting devices and the spin wave devices is probably an issue with the lack of gain. So we're all the way back to the beginning of the talk where Lilienfeld knew that you need gain, like that, meaning that the amplitude of the signal coming into a transistor, the transistor should be able to make a higher amplitude output, and that when you look at circuits, say you have a path of transistors that you have in a CPU, a logic path, and that so you're going between an AND gate and an OR gate and flip-flop and these different parts of logic. Well, you string everything from the input to the output, and you got like 20 transistors you have to go through from input to output. Well, if the signal reduces by noise or other, parasitic capacitances, things like that, you might not get enough signal out the other end unless there's gain. And so every time every time a signal goes through a transistor, it actually gets gained back up to a proper logic level, which we call in our modern designs power rails. So the whatever the 0.6 volts and the 0, it's always 0.6 and 0 because the transistor gain is used to push the output signals all the way up to the two levels. You don't have that in some of these beyond FETs, and that's going to be a big problem. Mott transition is a great example for a devices class where when you open up your semiconductor physics textbook, SZE is one of the big Bibles of semiconductor physics that we all have learned from in the big classes. One of the first pages, you come across this thing. It's called the independent electron approximation, and so all these formulas that you've been learning come from the simplified math of assuming that anytime an electron's going through a transistor, it never sees another electron, which is crazy, right? We know that they do, and in modern devices we have to deal with that. But that's all the simple math we can work with in textbook form comes from this independent electron approximation. Mott said, well, you know what? I bet that something interesting happens in some cases if you go through the hard math. So he did the hard math, and he came up with a theory that you could actually make an insulator switch to become a metal. So the band structure flips between having a wide band gap and having no band gap if you put enough electrons together. So a high enough current density. And won a Nobel Prize. So Mott transition's been a holy grail of device research. There are Mott devices. Vanadium oxide is a Mott material, and there are Mott transition devices made out of vanadium oxide. The problem with vanadium oxide is it has a phase transition. This meaning that it'll change the structure, like the grain structure. It'll melt in common language. I think at about 80 degrees C, and it only works in the phase of material that's above the 80 degrees C. So you have them. I think they're in some military, I don't know, rockets or something, but they're on top of heaters because they always have to be above 80 degrees to work. So a room temperature Mott transition is one of the holy grails that could get us. It's basically instantaneous. Moving the bands is instantaneous compared to moving cracks in a VRAM or what have you. All right, so let's get back to the timeline of the actual transistor. And it was 27 years between Lilienfeld's patent and the first transistor, which was a junction field effect transistor. Hope to maybe talk about the distinction here, but basically, no, I don't think there's a lot of junction FETs used today anymore. But Daisy and Ross didn't find a picture of them together, so I made one with AI. Same thing with Tala and Kong. So the MOSFET, the thing that we really have been using forever, that actually wasn't invented until even later, 1959. Now you're thinking. Every time I see one of these talks about transistors, everybody talks about 1948 and the Shockley, Bardeen, Brattain. That is a crazy story that amazingly gets forgotten, but Shockley was trying to make an FET. He was trying to make a field effect transistor, and he couldn't figure it out. So he got Bardeen and Brattain to start working on it. He actually went off to France for some conference or vacation or something like that. And Bardeen and Brattain are like, hey, let's see if we can do something before the boss comes back, because he was notoriously hard to work for. And they decided to switch to germanium. And germanium, the oxide, actually washes off in water. So they made a mistake and accidentally invented what's called a point contact transistor. So the actual piece of metal that they had probing down onto the silicon was enough to make a field effect and got him a Nobel Prize. Shockley, hard to work for, but super smart. He took that and went further with it and invented a type of transistor called a bipolar junction transistor. So this does not have an oxide, doesn't have a field effect, but is used today for various reasons, and I'm sure we'll talk about that. Crazy side story about what people normally talk about when they say the first transistor. What held everybody back was not understanding the materials. So this is like the purity of the materials, how important that was, the physics of the actual materials, and then surfaces. So all of our equations that we're going to talk about, for the most part, they're assuming infinitely big pieces of material where you don't have to worry about the edges. When you worry about the edges in real devices, and of course in the nanometer regime you do all the time, that's a whole other state of physics and what have you that very hard to understand and model and what have you. Now want to kind of get to how to put a system in place to innovate faster in what I call the angstrom era. So you've seen like the 18A from Intel. That's the angstrom is a unit that is 1/10 of a nanometer. So it's not a SI unit. It has been a very convenient unit because it's more like the atomic size. Marketing teams have grabbed it and we've moved off the SI units from nanometers to angstroms now, it looks like. But if you look at modern devices, so this picture I show here, I'm saying I don't remember. This looks like an MRAM, so these materials look like they're MRAM layers. But could very well be a two-dimensional semiconductor or diode or something. But in any case, a lot of it's going to be about the interfaces. Pauli, remember the name Pauli from last semester? I think Pauli exclusion principle, big guy in physics. So he has this famous quote, God made the bulk, but surfaces were invented by the devil. So we need to really, to accelerate learning of these novel devices. We're back basically in the day of Shockley, Bardeen, and Brattain, where it's new stuff, and we don't understand the physics, and we don't understand the surface issues and the materials. So we have just to accelerate that understanding. There's a lot of great new microscopy techniques that are really well suited. I'm, in this case, using an example of ARPUS. But there's a ton of new stuff. So we need labs that are equipped with the right equipment to get better data about how electrons move in materials, especially edge surfaces. We need better discovery of materials. So as we get data or ideas, we need to be able to simulate some fundamentals. And that is, there's a big field now is DFT, density functional theory. So this is basically going from what I think we're hopefully going to avoid true wave function talk in our series of classes, but electrons famously can be particles or waves. A lot of the physics that led to the band structure plots that you're looking at, the band gap, ECEV, that's actually coming through the understanding of electron as a wave and how it interacts with crystals. Let's just leave that alone. I barely understand that stuff. I barely understood that stuff when I was learning it at your age. But there's a new density functional theory which is looking at the probability density, so the quantum probability density, and that allows you to do some nice simulations of materials properties. So there's a lot of things we need to just do. We know how to do some of the stuff. We just need to integrate it and focus it and have common tools that can be used across researchers, not have everybody invent all their own stuff. Then once we have something that theoretically looks good and maybe as a proof of concept in a lab looks interesting, we need to quickly get it into advanced prototypes. So by advanced, I'm talking about the things that we care about from the product side is, can you make 1 billion of these things at 10 nanometer size? Do the properties scale from the micron lab dimension to the nanometer scale? When they scale, do you really get the energy and speed that you thought we were going to get? Because again, these are all going to have the same problems like the MOSFET, where you've got a great property. As you scale it to the nanometer regime, all the parasitics are not going to help you out. So you think you might have 100x improvement in something, memory speed, and you end up with a 10% improvement at the end of the day if you don't fully understand all of the things that go into making a modern product. So scalability, big issue. Statistics, we talked about the 8 sigma, so you can't measure 5 of these things in a lab as they have done it. You need to measure 1 billion of these things and show a designer, here's my distribution of what, resistance. And the designer will say, oh, I can make a sense amp. This is something that I could take the difference in the current between the 1 and the 0 and make it into a digital signal, for instance. And then reliability. So this is something that tends to not happen well in the early stage of a device, new device R&D, but really we should be able to make this more parallel in the evolution so that the end customer, and they all care about this, right? If Micron's going to buy your memory technology or Intel's going to buy your new transistor technology, it better last for 10 years when you send it to a customer. So there are ways to do this better and faster. Share costs among different researchers. So we just take 20 different universities that all do different versions of a ReRAM. There should be a standard chip. They don't all have to, this graduate student shouldn't have to figure out how to lay out a chip, do it wrong, spend a bunch of time. That should all be there. And there are ways to get nanometer patterning features into university labs as well. I was working on this, had this pretty much done in my last job where we would have say Intel and Micron have access to EUV tools, would create test chip or test structures at the nanometer scale, and then dice them up, cut the wafers up into pieces that the university researchers could deposit their films on, and then when they got data, they knew it was coming from nanometer features that they could never print in their own lab. And you can also do something called coring. So if you go to the lab up at the Pickle Research Center for UT. Most university research labs are running at 4-inch wafers. From cost standpoint of tools and everything, you can take a 300 millimeter wafer and just cut a 4-inch wafer out of that. In fact, multiple 4-inch wafers. That's called coring. So that's the program that we had all ready to go in my last job. And then along all of this, we can take all this data and we can put it into a comprehensive digital twin of a semiconductor process. And the beauty of a real digital twin universe is you can go from the atomic scale, zoom all the way out to the factory scale and back, and then people making machines that would deposit your material or etch your material, they can co-design their tools along the way as well. And you can really accelerate things. So digital twin, test chips, better lab. This is all things that I was trying to do in my previous job. New administration, different direction, and that's why I'm off. Looking for a new job now, because that's it's not that it's wrong. It's just different way to spend the money, and I want to spend my time doing this kind of stuff. Now. When we look at the last, I had those 3 ways. So improve existing transistors, come up with new transistors, and then the last way is re-architect the systems. And the big, knob that we have at the moment that everyone's exploring is the heterogeneous 3D systems. So I took this AI-generated picture from somebody's LinkedIn post. Basically, you can optimize different tiers. These are different wafers, chips, cut out of different wafers that optimize so you can make the memory better than the logic, that you don't have to deal with the CMOS compatibility issues that I talked about. You can make a lower cost layer in one versus the other. So you basically can have another degree of optimization that can really help. And if you look at this whole thing as a system, and then the underlying transistors down there are the technology. That is the System Technology Co-Optimization, STCO. That's a kind of industry buzzword at the moment. Previously, we did a lot of what we call design technology co-optimization. So we didn't have the system level. We'd have to think at the system level to optimize. But at least at the circuit level, we would be designing circuits that are optimized around the particular transistors that we were using. And what partitioning a system into chiplets, little tiny pieces, maybe incomplete chips is one way to think of a chiplet. So it's not a full CPU. It might just be the logic, or it might just be the memory. Anyway, we can break this into independent. We can break the full STCO into independent DTCO problems, and that allows us to optimize cost and power and speed in ways that we couldn't before. And if I want that 1500 degrees anneal now to make a better memory, I can do it, and the system will benefit. Now, you haven't erased system technology co-optimization, but I'm plugging this picture from this group called Semitech. This is a group of the researchers that were at NatCast, which was the public-private partnership that we had put together in my previous job that went away with the new administration's different use of the CHIPS funds. So I'm plugging these guys because they've kind of built up their own consulting group here, and they're experts in this kind of thinking. So we see this 3DHI already in products. So the AMD Zen 5 chip you see at the top, underneath that you can't see is the level 3 L3 cache dies on the bottom. So what AMD has done is partitioned, broken up the two pieces of logic and then memory, and they've done exactly what you would have predicted from these graphs. They've taken the 7 nanometer memory, which is the cheaper per bit, and put that on the back, and then they're using 4 nanometer logic, so advanced high density, high speed logic here. And it has a really big cost adder in addition to this, using just the flat lower cost, is the fact that if you had the memory and the logic together, memory, as I kind of talked about with the flash memory earlier, you often, when you make a memory, say you make 64 megabits, you're actually going to make 68 megabits. And you're going to have some dummy, some unused columns of bits. And then when you test your memory out of the factory and you get a defect, like a piece of dust has fallen on this particular bit and that bit doesn't work, you have ways of terminating the use of the defective column and replacing it with one of your spare columns called redundancy. And so memory, when you build in redundancy to the memory arrays, their yield is often 100% because you test it. You test each chip on the wafer, you find a few defects, you fix them with redundancy, and the chip now works. But if the cache memory is built into the logic and a piece of dust falls on the logic, then all the cache memory is 0 yield as well. So now by breaking this up into two pieces, the memory is now 100% yield where it was going to be 80%, just like the logic. And you save money just from the partitioning itself. And that pays for, conceptually, pays for the extra expense of the silicon, the through silicon vias, these TSVs, and the substrate. Those are not cheap, but pays for itself. In this case, AMD, for people buying this, they don't care much about the cost as the performance, but it pays a lot of dividends for other products. So back to this DAC, the Design Automation Conference. I spent a lot of time on this slide for the conference, and I will spare you a little bit here. Is the kind of EDA problems you have that that come along with the party when you do this partitioning and heterogeneous 3D-HI, which is getting power in and out of layers that where they might be. When you have one layer, you can put a gigantic piece of metal as a package on the top for a heat sink and pull the heat out. But a chip in the middle is not going to have that advantage. It's got to communicate heat through another layer. That's a problem. Getting power through layers to other layers, big problem. Also, do you know where all these chiplets came from? And can you prove it to me? The system person needs to know the trust and the provenance of everything, of the chiplets. Now, you put a system together, it doesn't work. Who owns the problem? It's going to be a bunch of finger pointing. It's going to be a big issue. Modeling the cost, of course, is super important and more difficult when you work in this regime. The chip fails. right? Who owns the, something went out of timing. Whose layers, what layer problem was it? When you make a logic die, you put in test circuits, typically self-test circuits, so the chip can power on and give you basic idea that, hey, I'm working. I probably don't have a defect. Or you externally, put probe tips down and you test the die. But one way or another, you get to what's known as KGD, known good die. So I've tested this, and as I ship it to you, Mr. Customer, I stand behind this chip and it works. You can put it in your system. Now, if you break the logic and the memory into two different layers, neither one is a functional piece of it, fully functional piece of a CPU. So you don't know for sure that that thing is working until you put it together and have spent all your money putting it together. So another issue that the EDA community can help with, which is tied with sort. So, I've got the way that, say, Intel works is due to statistical variation, let's call it, primarily gate length variation, the chips that come out with shorter gate lengths, but within the expected range, are going to be faster. And the chips that come out with longer gate lengths are going to be slower. So what Intel does is they sort through the testing of the die. They sort them. The fastest ones get sold for the most money, and the slowest ones get sold for less money. In this case, what I mean by sort is, you're assuming that a chip is going to be in spec, but once you have multiple layers with multiple specs moving around, it becomes a little more complicated. So that's what I meant by that. So spare you a lot of details, but that's the tie-in here at the end of the talk with the audience that I have here. And then my conclusion to talk about, we've been through 100 years of the FET. I think, yes, the FETs will still be used 100 years from now. I don't think they will be what we use for, leading edge computing, but they're basically free at this point and highly reliable. It's kind of like the car, right? Cars have been around for a long time. We still use cars. Shortly, I think, in the grand scheme of things, we'll be zipping around in vertical takeoff and landing taxis, but there will still be cars. At the same time I say that, the world desperately needs the acceleration of something better than the FET, because fundamentally, field effect means you have to put a voltage on a gate, and you have to bring the parasitic capacitance of all the wires attached to that gate also up with you. That doesn't scale, and that's a power problem that you just can't solve when you have a moderately high voltage that you need to get to. So we need something that is lower voltage or fundamentally different than the FET. And then I went through this briefly with y'all, but what is enabled by the EDA is, really putting together tight systems of software along with hardware validation that can really accelerate the materials to systems exploration. We need this to be not 30-year trails, and needs to be more on the 10-year horizon before data centers consume all of the energy on the planet. And then the 3D-HI, so 3D heterogeneous integration. CMOS plus X is a buzzword where it's basically, we know everything at the end of the day still needs CMOS. That's the fundamental, known, reliable way to do computing. But then on top of the CMOS, physically on top in the case of 3D-HI, you could have an analog neuromorphic circuit. We'll talk about that. So you can do computing. Neuromorphic just means brain-like. So the neurons in our brains are not ones and zeros. They change resistance. So the ReRAM, you can use ReRAM to make something that looks a lot more like the way the brain works. People are excited about that. Just haven't made it work. But you can envision various things X, could be photonics, whatever, that are physically glued onto a CMOS backbone and allow the communication between systems to still be what we know and love. CMOS 2.0, I glossed over that, but that's the IMEC branding of 3D-HI system technology co-optimization. So it's kind of, I think it's kind of becoming a buzzword in the industry, so I used it here. So that was my 20-minute talk, which for you was an hour and 24. So thanks for listening, and remember your homework assignment. I hope you were thinking that through when I was talking, and maybe can highlight things you think are important that you don't understand well, and we can use that to to help us along in the course. And I'll see you virtually next week.